created by MindSticks Foundation Trust. Welcome, students. So glad you could join today's masterclass. We're going to be methodically examining the absolutely fascinating world of chemical reactions. I'm literally thrilled to be your guide today as we break down these vital concepts. You know, chemistry is everywhere around us. By the end of this explainer, you're going to have a crystal clear understanding of exactly how different elements and compounds interact to just change the world we live in. All right, let's dive right in. Please quickly note down today's agenda in your notebooks. We'll be covering, number 1, types of reactions, 2, endo and exothermic processes, 3, rates of reaction, 4, oxidation and reduction, and finally, 5, corrosion and rancidity. We've got a beautifully structured journey ahead of us today, so let's stay focused. Right, Section 1, types of chemical reactions. Let's begin our very first chapter by discussing the fundamental ways chemical compounds interact with one another. Now, there are a few ways reactions occur, but today we're really going to master displacement and double displacement. Okay, let's unpack this first definition, the displacement reaction. You can think of it kind of like a stronger, more energetic wrestler taking the place of a weaker one in the ring. We previously saw in our textbook that when zinc dust is added to a blue-colored copper sulfate solution, suddenly a colorless solution of zinc sulfate is formed. Why does that happen? Well, it's because zinc is more reactive. It completely displaces the copper. And that's the exact definition of a displacement reaction, a more reactive element taking the place of a less reactive one. Now, this rule absolutely applies to other metals too. Just like zinc, elements like iron, symbol Fe, and lead, symbol Pb, are actually more reactive than copper as well. Because of that, they can also displace copper from its compound. For your exams, you must, and I mean absolutely must, know how to complete these reactions. So iron plus copper sulfate will yield iron sulfate and copper. It's just a simple swap based entirely on reactivity. Let's move on to our next type and see how this builds up. What actually happens when two compounds mutually exchange their ions? Well, if ions are mutually exchanged to form a solid that settles right at the bottom of the test tube, which, as you know, we call a precipitate, this is known as a double displacement reaction. Basically, both partners are swapping places. Let's do a quick recall of our laboratory activities just to test your memory. When we mixed a solution of potassium chromate into a solution of barium sulfate, a reaction took place. Do you remember what the color of the precipitate formed was? And think about it, would you call this reaction a displacement or a double displacement? Since two compounds are reacting to form a brand new insoluble solid, it is, of course, a double displacement reaction. Moving right along to Section 2, endothermic and exothermic processes. Let's turn our attention to how heat plays a really critical role in both physical changes and chemical reactions. Students, please make sure you note down this strict difference in your books because it is a massive favorite for exams. Endothermic processes absorb heat from the outside surroundings. This literally means the temperature of the resulting solution drops. It feels cooler to the touch. Melting ice, for instance, is a physical endothermic change. On the flip side, exothermic processes give away heat. The temperature actually increases. A super crucial example of an exothermic reaction is the dilution of concentrated sulfuric acid. A massive amount of heat is liberated instantly. Because of this, the golden rule is we must always add acid to water very slowly while stirring. Never, ever add water directly to concentrated acid or you risk some very dangerous splashing. And we can actually illustrate this concept quite practically in the lab. Why do we use plastic bottles for this heat exchange experiment? Well, because plastic acts as a great insulator and prevents the heat from just dissipating away. When you add potassium nitrate to the first bottle, it absorbs heat from the water, making the bottle noticeably cooler. But when you carefully add sodium hydroxide to the second bottle, heat is given out, making that bottle significantly hotter. It's simple, it's safe, and it perfectly illustrates the point. Okay, Section 3, rate of chemical reactions. I want you to think about your daily life for a second. Why does milk set into curd much faster in the hot summer than it does in the cold winter? Or why does cooking gas start burning the instant you ignite it, while an iron article takes months to rust?
It turns out there are exactly 5 primary factors deciding how fast a reaction occurs. Number 1 is the nature of the reactants. For example, aluminium is just naturally more reactive than zinc. Number 2 is particle size. If you drop solid chunks of Shahabad tile into acid, it dissolves quite slowly. But if you crush that exact same tile into a fine powder, it reacts very rapidly because those smaller particles offer way more surface area. Number 3 is concentration. Concentrated acids will always react faster than dilute ones. Number 4 is temperature. Heating things up speeds up the reaction, just like setting curd in the summer. And the fifth, well, that's the really fascinating concept of a catalyst.
Speaking of that fifth factor, let's look at the decomposition of potassium chlorate. On heating, it breaks down very, very slowly, and interestingly, neither changing the particle size nor increasing the temperature helps much here. However, if we simply add a little bit of manganese dioxide powder, the potassium chlorate suddenly decomposes rapidly to liberate oxygen gas. The truly magnificent thing here is that the manganese dioxide itself undergoes absolutely zero chemical change. It's just there to help. And that's your definition of a catalyst, a substance that speeds up a chemical reaction without actually participating in the chemical change itself. Let's move to Section 4, Oxidation and Reduction. We're now turning our attention to one of the most vital pairs of reactions in all of chemistry. These are happening everywhere, literally from inside our own bodies to massive industrial factories.
Now, the definitions are actually quite simple to memorize. Oxidation happens when a reactant combines with oxygen or when it loses hydrogen. In deeper ionic terms, it also means losing one or more electrons, kind of like ferrous ions turning into ferric ions. Reduction, on the other hand, is the exact mirror opposite. It's when a reactant gains hydrogen or loses oxygen. Simple enough, right? Gain oxygen, oxidation; lose oxygen, reduction.
Consider this classic reaction. When hydrogen gas is passed over black copper oxide, a reddish layer of copper is formed. So what's exactly happening here? Well, the copper oxide loses its oxygen to become just copper, and losing oxygen is reduction. At the exact same time, the hydrogen gas gains that oxygen to become water. Gaining oxygen is oxidation. When oxidation and reduction happen simultaneously in the exact same reaction, we just merge the words together and call it a redox reaction. Redox, reduction, oxidation. Finally, Section 5, Corrosion and Rancidity. Students, we absolutely must examine how these oxidation reactions affect our everyday materials and food items. You see, chemistry isn't just locked away in the lab. It's right there in your kitchen and in your garage. Let me ask you a practical question. Have you ever noticed how brand new, shiny two-wheelers or iron gates look absolutely spectacular at first, but over time, they kind of lose their shine? They eventually acquire this flaky, reddish-colored solid layer. Why exactly does this happen? Well, a simple 4-test tube experiment perfectly demonstrates the answer. If you place iron nails in different environments, you'll find they only rust when exposed to both air and water. A tube with just salt water rusts fast. A tube with just dry air, no rust at all. Rusting is actually a really complex electrochemical process. The iron oxidizes at the anode region to form a hydrated iron oxide, which we casually call rust. And honestly, this simple reaction causes tremendous damage to infrastructure worldwide every single year.
But it's not just metal that oxidizes. Just as metal corrodes, our food gets damaged too. When leftover cooking oils, fried foods, or vanaspati ghee are left exposed to the air for a long time, they undergo air oxidation. The actual chemical structure changes, which causes a very foul odor and a pretty terrible changed taste. In science, we term this specific oxidation of food as rancidity.
So, I'm going to leave you with this final thought exercise to test your understanding of today's masterclass. Knowing that oxygen in the air is the main culprit behind rancidity, what practical methods will you use at home to protect your favorite fried snacks? Will you use chemical antioxidants? Maybe flush the bags with nitrogen gas, or simply store them in airtight containers? Think about how chemistry empowers you to make these smart, everyday decisions. Thank you so much for your sharp focus today, students. Keep revising these fundamental reactions, and I will see you in our next explainer.